Okay, so for our first revision video, we're going to be having a look at Trigonometry 1, because very soon we're going to be having a look at Trigonometry 2 in the class. So what we're going to revise here is we're going to revise radian measure, the sine, cos and tan of different trigonometric functions. We're going to have a look at the unit circle, the area of a triangle, the cosine rule and the sine rule. So hopefully you look at this video and you revise these topics because you are definitely going to need them in our Trigonometry 2 course. Alright, so let's get started. So the way I'm going to do this video is basically I'm going to revise over the topic first, and then either in this video or in a part 2 of this video, then I'm going to do example questions and exam paper questions. But I'll still do some example questions in this one as well. We're going to start with radian measure. So basically, up until this point you're used to measuring angles in degrees. So for example, you will have had triangles before and you'll have measured this angle here, say as 30 degrees, or you might have had 60 degrees, and you all know that a full circle is 360 degrees. So what is this thing here then, radian measure, all about? Well, degrees aren't the best tool to use for when we're doing trigonometry and certain parts of calculus. We want to use a measure of angle called radians, and basically radians relate the length of the radius to the angle at the centre. 360 degrees is kind of an arbitrary number. If you think of it as 365 days in the year, one full circle, 360 degrees, so it doesn't really mean anything. Why is 90 degrees a right angle? You know, so we want to come up with a much more accurate way of measuring angles, and that's where we do radian measure. So if you want to think of a circle which has a radius of r, well, if I create an arc here which is the same length as that r, that radius, well then I've created an angle at the centre which is said to be 1 radian. If I was to create an arc that was 2r long, well then I will have created an angle at the centre or so this would now be 2 radians, this angle at the centre. So basically the angle at the centre measured in radians is directly linked to the radius of the circle. So remember, if the length of that arc is the length of 1 radius, well then we have 1 radian. If the length of that arc is 2 radii, well then this angle here is 2 radians. And if you want to think about it this way, I could keep going with this. 3 radians as the length of the arc will be, or sorry, the length of the arc being 3 radii will be 3 radians. So in other words, if I divided the length of the arc by the radius itself, I have 1. In this case I have 2r divided by r is 2. The next one will be 3r divided by r is 3. So in other words, if I divide the length of that arc by the radius, I will have the angle in radians. Now just try and remember, this is a revision video. It's not, I'm not teaching you this for the first time. This is revision for the Leaving Cert. So the length of the arc divided by the radius gives me the angle in radians. You all know that the length of a full circle from Junior Cert, the circumference is 2 pi r. So the length of the full circle is 2 pi r. So that means the length divided by the radius would be 2 pi r divided by r, which gives us 2 pi. So the angle of a full circle is 2 pi radians. You know that a full circle is 360 degrees. So 360 degrees must be 2 pi radians. And using that basic statement, I can find basically any angle. Pi radians dividing both sides of this by 2 would give me 180 degrees. Pi divided by 2 would be 90 degrees. Pi divided by 3, which is basically 180 divided by 3, would give me 60 degrees, and so on. So there are plenty of angles there that you can measure out yourself. I don't have to do a load of them, but there are certain ones that we come back to again and again and again, and they're known as your special angles. And you need to know the sine, cos and tan of these special angles, but I'll get to sine, cos and tan in a second. So if you want to think about it, 0 degrees is 0 radians. 30 degrees is pi over 6, or 180 over 6 radians. 60 degrees is pi over 3. 90 degrees is pi over 2. 180 degrees is pi. 270 degrees is 3 pi over 2. And then 360 degrees is 2 pi radians. So they're basically the conversions between degrees and radians, but just if you remember this one, you can basically convert any of them. So just remember that one. 360 degrees is 2 pi, and from that you'll work out any of them then. Okay, let's have a look then at the next part, which is the length of an arc. Alright, so we know that the angle in radians is the length of the arc divided by the radius. Remember? The radius, the length. So the angle in radians is the length of the arc divided by the radius. Rearranging that, multiply both sides of the equals by r, and we have the angle multiplied by the radius will give me the length of the arc. So that's a formula that will come in handy for us. The length of that arc there is the radius multiplied by the angle, but very careful, that angle must be in radians, not degrees. Alright. These formulas are in the table, so, but again, I've told you a million times, it's better to know them than to be going looking for them. So that's the length of the arc. Alright. The next important one is the area of a sector. Again, it's very straightforward if you use your logic. Let's do this as if we were dealing with degrees again, just because you actually do know it. There's a circle, and there's a slice of that circle. Okay, like a slice of pizza, it's a sector. Okay, so that's a sector. And if we want the area of that sector, well, think about it this way. If this was, let's just make up, this was 60 degrees, you know that the area of the full circle is pi by r squared. So we don't have the full circle, we have a fraction of the full circle. It's not half of it, it's not a quarter of it, but it is a fraction of it, and the specific fraction we have 60 360ths of it. 60 degrees out of 360, so that's the fraction we have of pi r squared. Now 60 over 360 is the same as saying a sixth pi r squared. So no, we don't have the full circle pi r squared, but we do have a sixth of it, so we have a sixth of pi r squared. So that would be the area of that sector. It's the angle in degrees over the full angle. The angle in degrees over the full angle multiplied by pi r squared. So in radians it's going to be the same thing. It's going to be the angle in radians that we have divided by the full thing, which we know is 2 pi because 360 degrees is 2 pi, multiplied by pi r squared. But there's a bit of cancelling that can happen here because pi divides into that pi, leaving 1 remainder. So what we have is theta r squared over 2, or the way it's normally written, a half r squared theta, and that's the area of a sector. So that's basically a couple of important things there. I'm just going to sum up those 1 or 2 things that we've done up to that point there. 360 degrees is 2 pi radians. The length of an arc is given by the formula r theta, in other words the radius of the circle multiplied by the angle in radians. And the area of a sector is a half by the radius squared by the angle in radians. And please remember that for either of these two, the angle is in radians, okay? So that's where we're at the minute. So if you want to see a quick example of one of these working, let's convert 2 pi over 5 radians to degrees. Alright, so 2 pi over 5 radians. We know that 2 pi is 360 degrees. Okay. That means pi is 180 degrees, dividing both sides of that by 2. But I don't want to know what pi is. I want to know what 2 pi over 5 is, or 2/5 of pi. So if I get 2/5 of pi, I multiplied the left by 2/5. So what do I have to do to the right? I have to multiply the right by 2/5. And basically that's going to be 2 by 180, which is 360. And then 360 divided by 5, that's going to be 72 degrees. So it's basically going to be 360 over 5, which is 72 degrees. So 2 pi over 5, or 2/5 pi, is 72 degrees. And all we used was this one thing which we said to remember. 2 pi is 360 degrees. Okay, what about changing an angle in degrees into radians? So let's random 55 degrees. 55 degrees in radians. So what we know is that 180 degrees is pi. But I don't want to know what 180 degrees is, I want to know what 55 degrees is. So the easiest thing to do is to find out what 1 degree is. Dividing both sides of that equation by 180, I have 1 degree is pi over 180. So if 1 degree is pi over 180, well then 55 degrees must be 55 times bigger than that. So multiply both sides by 55, and I have 55 pi over 180. Now 55 pi over 180, it will simplify. 180 divided by 5 is 36, so we're going to have 11 over 36 pi. And then there's not really anything then that you can do from there, so it's going to be 11 over 36 pi. Now you can change that to a decimal if you want. So it's going to be 0.31 pi, but I'm just going to leave it as 11 over 36 pi. So again, the only thing we needed to remember, and I started with 180 equals pi, but you can start with 360 equals 2 pi, it's the same thing. But that was just that one piece that you had to remember. So that basically finishes up the section on radian measure. There are examples in the book that you can try. The questions for that are on page 35, and there are a good few of them, and I will get to some of them, but if you want to try them yourself, and then if you're stuck you can ask me in the class. But I don't think you're going to have an issue with any of them, and plus you've done them all before. Remember, the solutions are up on Google Classroom as well. So okay, move on. So we're going to have a look now at trigonometric ratios. So and you know these as sine, cos and tan. Okay, and as for where the words themselves come from, whether they're from Latin or Greek or ancient Arabic, it's all different, but basically they mean similar things, where this is something that means something similar to a bowstring or something like that. That's your sine. Cosine is the complement sine, basically the sine of the complement angle. In other words, here's a triangle. If this angle here is A, well then the angle up here, this one, well that's going to be 90 minus A in a right angled triangle. So they're known as complement angles of each other. So that's why it's known as the complement sine, or the cosine, or cos. So it doesn't really matter where the words come from. Basically, the sine of an angle is the cosine of its complement angle, basically. And then tan is your tangent, your line that touches the circle at one point. So we have three ratios, sine, cos and tan, and the important thing about them is that if I have a right angle triangle, no matter the size of the triangle, it's the angles that determine the ratios. It's only the angles. Okay, like I can have an angle here of 60 and an angle here of 30, making this 90. And even in a larger triangle, I know this isn't drawn to scale or anything, but if this angle is 60 and if this angle is 30, well then the ratio of this side to this side, or the ratios are going to be the same. It's the angle that's important in the triangle. Okay, so basically this side here divided by this side will be the same as this side divided by this side. Okay, they have the same ratio as each other, and that ratio is known as the sine of the angle 60 degrees. Whereas if I were to do this side divided by this side, it will be the same as this one divided by this one. The ratio is the same, and that's known as the cosine, because basically the cosine of 60, which is what this one is, should be the same as the sine of 30. The sine of 30 is opposite over hypotenuse, which is what cosine is. They are complement angles to each other, which is where the word cosine comes from. They're complement angles. So I hope I'm explaining that enough, but again, this is a revision video, it's not an actual class. Alright, so yeah, like I was saying, 60 degrees is 90, or sorry, not 60 degrees, 30 degrees is 90 minus 60. this angle here and this angle here are complement angles to each other. Okay, so basically you have 6, there are a few trigonometric ratios, there's 6 that we'll deal with, but there's only 3 I'm going to talk about now at this minute. We have our sine, our cosine, or cos for short, and our tangent, or tan for short. The sine in a triangle is the opposite side divided by the hypotenuse. The cosine is the adjacent side divided by the hypotenuse. And the tan is the opposite divided by the adjacent. And what do I mean by opposite, adjacent, hypotenuse? The hypotenuse is always the side that's the longest. And if you're unsure which side is the longest side, it's always the side that's opposite the 90-degree angle. Always. Okay, so that's your hypotenuse. H in these examples, okay? Now, opposite and adjacent depend on what you're talking about. Are we talking about the angle A? If so, A, this side here is the opposite to A, making this side its adjacent. Whereas if I was talking about the angle B, just draw this out again. Well, if I was talking about B, that would make this the opposite and this the adjacent. But this is always the hypotenuse because the hypotenuse is fixed. It's the longest side and it's the side that's always opposite the 90-degree angle. So we have our 3 ratios, sine, cos, and tan. The sine is the opposite side divided by the hypotenuse. The cosine is the adjacent side divided by the hypotenuse. And the tan is the opposite divided by the adjacent. So you might get a question something similar to this. They might say to you, tan B equals root 5 over 2. And they'll say to you, find sine B and cosine B. Well, you might be tempted to start getting your calculator out and saying what's root 5 over 2 and then getting inverse tan and so on. That's a bit too complicated. Don't even be thinking of that. Basically, draw yourself a triangle. A lot of these problems can be solved with a simple picture. And I always recommend you draw a picture. So you have your right angle there, which means that this is the hypotenuse. Alright, now let's just label this angle B. Now remember, tan is opposite over adjacent. And in this case, that's root 5 over 2. So that means the opposite side to B is root 5 and the adjacent side is 2. Okay, the opposite, root 5, the adjacent, 2. And you might be saying, what if I drew my triangle the other way around? What if B was the angle at the top? It doesn't matter. It'll be the same thing anyway. Let's draw this out again. Let's say that this is B. This is the hypotenuse because there's our right angle. That makes this the opposite, root 5. And that makes this, the adjacent 2. But it doesn't make a difference. Anyway, we were asked, what's sine B and cosine B? Remember, sine is the opposite divided by the hypotenuse. So the sine of B will be the opposite, which is root 5. Divided by the hypotenuse, which, oh no, hold on a second, we don't know the hypotenuse. So we need to figure out the hypotenuse. Remember, this is a right angle triangle, and you should know by now that anytime we see a right angle triangle, we're definitely going to be either doing something with sine, cos, or tan, or else Pythagoras' theorem. And in this case, it's going to be Pythagoras' theorem. I'm going to use Pythagoras' theorem to just help me, I'll do that line again, to just help me figure out what the hypotenuse is. So I'm not going to go through revising what Pythagoras' theorem is. we know that the 2 squared plus the root 5 squared should give me the hypotenuse squared. That means 4 plus 5 will give me the hypotenuse squared. 9 is the hypotenuse squared. Get the square root of both sides and we have hypotenuse is 3. So basically we don't have to write h by p here anymore. We can fill that in, it's 3. So sine is opposite over hypotenuse, so it's going to be root 5 over 3. The cosine of b is the adjacent over the hypotenuse, so that's going to be 2 over 3. So there we go. The only maths we needed was Pythagoras' theorem. There was no calculator needed whatsoever. You have the tan of b, you have the sine of b, and now you have the cosine of b. So I mentioned earlier on, I'm going to zoom back up to it really quickly there just so you can see it. I mentioned earlier on that we come across these angles again and again, and they're known as special angles, and that you should learn these. They're on page 15 of the tables, but it's still a good idea to learn them. But what you'll also need to know is the sine, the cos and the tan of those special angles. And to help us do that, basically we just need 2 triangles. So I'm going to just draw out 2 triangles here. Alright, this one here, if I can draw it, how many was that, 6, 7, 8? I'll just do it roughly, something like that anyway. This one here is an isosceles triangle, which means both sides here are the same length. And that length is 1. So it's a triangle where both sides are 1 and 1. Just like in the last example, if I use Pythagoras' theorem, I can figure out that this length over here, the hypotenuse, will be the square root of 2. Remember, the important thing about isosceles triangles is not only are the sides the same, but the angles here are going to be the same as each other as well. And if this one over here is 90, that means this one and this one together need to be 90. So if they're both the same and they both have to add up to give 90, well then they both must be 45 degrees. So all I've said so far, all we needed so far was to draw a triangle, an isosceles triangle where 2 of the sides have a length of 1. From that I've worked out every other number using Pythagoras' theorem and what we know about geometry. So I have a triangle here. Now let's get the sine of 45. And let's pick this one for now. Sine is opposite divided by hypotenuse. This is the opposite. 1 divided by the hypotenuse is root 2. What if I had used this angle up here as the 45? Well, the sine of that would be the opposite, which is 1, divided by the hypotenuse, which is root 2. So it gives me the same answer, so it doesn't matter which 45 I take. The sine of 45 is 1 over root 2. Let's have a look at the cosine of 45. Cos is adjacent over hypotenuse. So if we look at this angle, this one's adjacent. This one's the hypotenuse. So it's 1 over root 2. And the same if I had gone for this 45, it would have given me the same thing. Now let's look at, let's look at the tan of 45. The tan, let's take this angle. Tan is opposite over adjacent, which is 1 over 1, which is 1. So 45 is one of our special angles. And now we've worked out that the sine of 45 is 1 over root 2, the cosine of 45 is 1 over root 2, and the tan of 45 is 1. Now let's draw one other triangle. This time one of the angles will be 30 and one of the angles will be 60. So if I make this one 60, this is 90, that means that has to be 30. The lengths of the sides are going to be 1, 2, and root 3. So let's do sine, cos and tan. Sine 60 is the opposite, which is root 3, over the hypotenuse, which is 2. And just before I go any further, I'm just going to do the cos of 30, because remember, that was the sine of 60. 30 is the complement angle to that. So the complement angle, it should be the same answer. The cos of 30 should be the adjacent, which is root 3, over 2. And they are the same answer, because the sine of 60 has to give me the same as the cosine of 30, because 30 and 60 are complement angles. And that's what cosine means. It's the complement sine. So if sine 60 is root 3 over 2, well then cosine 30 has to be root 3 over 2. Let's have a look at the sine of 30 degrees now. Sine 30 is the opposite over the hypotenuse, which is a half. Alright. And let's get the cosine of 60, which is the adjacent over the hypotenuse, which is a half. And again, that makes sense because 30 and 60 are complement angles, so the sine of 30 should be the same as the cosine of 60. And then the last one we have is the tan of 60, which is the opposite, which is root 3, over the adjacent, which is 1, so that's just root 3. And the tan of 30 is the opposite over the adjacent, which is 1 over root 3. So there we have it. There are special angles, 30, 45 and 60 degrees. And you should know the sine, cos and tan of all three of them. They are in the tables, but it's much better to know them, because if you're simplifying a question and you see root 3 over 2 popping up, you will know that that's 30 degrees, so it might lead you to the next step. Whereas if you don't know it, you won't know to look for it in the tables. So that's where we're at now with our special angles, 30, 45 and 60 degrees. And again, you can try some examples yourself on page 40 of the book. But I'm just going to stop it there for now with that one, and then I'll move on to the unit circle. So just go. So up to this point, you've basically learned how to get the trigonometric ratio of an angle up to 90 degrees. But what we're going to do now is we're going to look at getting the trigonometric ratio of an angle between 0 degrees and 360 degrees. So we'll be able to find the sine, the cos or the tan of an angle that's between 360 degrees or 0 degrees. So how do we do that? We use what's known as the unit circle. So basically what I'm going to draw here is I'm going to draw an XY axis. And on that axis I'm going to do my best to draw a circle. We'll go 4 units to here, 4, 4, 4. And I'll do my best to draw as accurate a circle as I can. It's not very good, but it'll do for what we have to talk about. So this is known as a unit circle for a very important reason, and that reason is that the radius of this circle is 1 unit. So basically the distance from here to here is 1 unit long. From here to here is 1 unit long. I'll actually do that in a different colour just so you can definitely understand what I'm talking about. The distance from here to here is 1 unit long. In fact, the distance from the origin to any point on the edge of the circle is 1 unit. So this distance is 1, this distance is 1, this distance is 1, and so on. So why is that important to us? Well, the reason that's important is because if I know that the length of that red line is 1, that means that the point where that circle intersects the x-axis are the coordinates 1, 0. And this point up here where the circle intersects the x-axis, that's the coordinate 0, 1. And over here we have minus 1, 0. And down below we have 0, minus 1. So, how is this going to help us to find the sine, cos or tan of an angle that's between 0 and 360 degrees? Let's just have a look at this first quadrant here, and I'm calling it a quadrant because the circle seems to be divided up into 4 sections. So I'm going to have a look at this quadrant here in particular. So let's draw out an angle. I'm going to start on the positive x-axis, and to make an angle I'm either going to have to move clockwise or anti-clockwise. And just to go along with convention, which is what most people do, I'm going to call it a positive angle if I go counterclockwise. And it will be a negative angle if I go clockwise. So just try to remember that. I'm going to be going around in a counterclockwise direction. So if I'm starting on the positive x-axis, let's say I move around this much. What I will have done, just for the sake of this diagram, I just want to make that smaller. So I've moved around this much, creating an angle theta. So that's a positive angle because we've decided that counterclockwise will give us positive angles. Now, you can actually get the sine, cos or tan of that angle by turning it into a right angle triangle. I haven't affected the angle in any way, so basically if I want to get the sine, the cos or the tan of that, I just have to use the ratios which we used before. Opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent for tan. So how does that help us? Well, the distance, what is the length of the hypotenuse in this circle? That length there. Because the radius of that circle is 1, it's a unit circle, remember. Because the radius is 1, that means the length of the hypotenuse is 1. Now this is some point x, y. So what is the length of that purple line there? This line, what is the length of that line? Well, it's going to be the same as the length of its image on the y-axis. For example, let me just highlight there. Wherever that point is there on the y-axis, that's the same length as the purple line. We don't know what that point is on the y-axis, so I'm just going to call it y for now. And the same is going to be true of our line on the x-axis. This length here, well actually I'm overlapping too many colours here, but the green part, well that's going to be wherever this x value is. So the length of that line will be x. So if I zoom out just to give us a bit more space, I know the writing's getting a bit harder to see there, so I'll just bring it back up to its regular size. What you know is that the sine of that angle theta should be the opposite over the hypotenuse, which in this case will be y over 1. Now sine theta, y divided by 1 is just y, so sine theta is y. I can do the same for cos. The cos of that angle theta is the adjacent over the hypotenuse, which is x over 1. So cos theta is x. So in other words, if you look at this coordinate here, x, y, the x coordinate will be the cos of that angle theta, while the y coordinate will actually be the sine of that angle theta. This helps us because now I know that whenever I go around my unit circle, Whatever the x coordinate is of the point where I land on the circle, that will be the cos of my angle theta. And whatever the y coordinate is of when I go around my circle, that will be the sine of the angle theta. Now, at this stage, you should remember that tan is opposite. We'll do this in a different color blue. Tan is the opposite over the adjacent. So in other words, the tan of our angle theta will be the opposite, which is y, over the adjacent, which is x. Or in other words, as you know already, sine theta over cos theta. So tan theta is y over x. So we're going to highlight all three of them. And we're going to show how this can be useful for helping us find the sine cos angle between 0 and 360 degrees. So what we'll do is I'll just take this as reference, copy and paste it. I'll take this, copy and paste it. And then we'll take this, copy and paste it. So we'll use them as reference at the top of our page. So remember, sine theta is y, cos theta is x, and tan theta is your y coordinate over your x coordinate. So let's redraw ourselves a unit circle. So again, I'll try my best to draw as accurate a circle as I can. Try to keep the radius the same. So I think it's a bit better than the last one, but still not the best. Okay, and what I'm going to do is I'm going to rewrite my coordinates here. Sorry, I want red, not brown. So this was the coordinate 1, 0. This was minus 1, 0. This was 0, 1. And down here we had 0, minus 1. So remember, we're going to start at the positive x-axis here. And we're going to move around in a counterclockwise direction. So I'm going to move around, and let's say I move around so much that I end up at the very top up here. Now the angle I've created, theta, that means I've created an angle of 90 degrees. So what is the sine of 90 degrees? Well, as you can see up above, the sine of 90 is the y coordinate at that point. And the y coordinate at that point, up here, is 1. So that means the sine of 90 is 1. The cos of 90 degrees, well, cos is the x coordinate of the point where our angle meets the axis. So the cos of 90 degrees is going to be the x coordinate, which in this case is 0. So the cos of 90 is 0. And lastly, the tan of 90 is going to be our y coordinate over our x coordinate, which in this case is 1 over 0. And you might realize that we cannot divide by 0. So basically we have something which is undefined at this point. And if you want to check that out on your calculator, you're going to get the same message. I'm just going to check and see exactly what message my calculator gives me here. Error. It's giving me a math error. So basically we have undefined for a 90-degree angle, but other angles will be different. We will be able to get a tan for other angles. So basically what you will see is the sine, cos or tan of any angle in this first quadrant is going to be positive. They're all positive. Now, if I wanted to get the sine, cos or tan of an angle in the second quadrant, and let's just give that a different colour. Oh, sorry, highlighter. So if I wanted to get the sine, cos or tan of an angle in the second quadrant, just colour that in there. Well, to do that, let's just say, here's my angle. Now we measure off the positive x-axis, so technically this is the angle here which I'm looking at. But that's an angle greater than 90 degrees, and we can't use opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent to figure that out. But what we can do is, to get to that point, it's the same as if I just took this angle from the negative x-axis. It still brings me to the same point. So this angle here is what's known as my reference angle. I'll just write that down here. This is my reference angle. I'll come to that again in a few minutes, but basically the sine of whatever this angle is going to be the x coordinate, or sorry, the y coordinate. Now at this point the y coordinate will be positive. So in quadrant 2 the y coordinate is positive, so that means the sine will be positive. You can see that the cos is the x coordinate. Now no matter what angle we have in quadrant 2, the x coordinate is going to be negative because we have a negative x value. So the cosine is going to be negative in this quadrant. And remember, tan is our y divided by our x. So tan is a negative divided by a positive, which is negative. So in quadrant 2, the only thing that works out to be positive is actually the sine. So what I can do, I'm going to get rid of these colours for a second. So in quadrant 1, they were all positive. And in quadrant 2, the only thing that's positive is the sine of the angle. Now let's have a look at quadrant 3. We'll do that in green. So, quadrant 3. Well, no matter what the angle, let's just draw ourselves an angle. Remember, this is the full angle, but again, because this is greater than 360 degrees, I need an angle which I can get the sine, cos or tan of. So I'm going to use my reference angle, and my reference angle will actually just be this one, because it's still going to bring me to this point. So this will be my reference angle, but I'll have to take into account what is our sine going to be. Is it going to be positive or negative? So let's have a look in quadrant 3. In quadrant 3, the sine of this angle here is going to be the y coordinate, and the y coordinate is negative in quadrant 3. The cos is going to be the x coordinate, and in quadrant 3 the x coordinate is negative. And tan is our y coordinate divided by our x coordinate, which will be a negative divided by a negative, which is positive. So we've just figured out that in quadrant 3, the only positive ratio is the tan ratio. And lastly, we're going to move into quadrant 4. So, quadrant 4. Sine is our y coordinate. And let's pick any angle. This angle here. Well, our y coordinate is going to be negative. In quadrant 4, y will be negative. Our cosine is our x coordinate, which will definitely be positive in quadrant 4. X is a positive number. at this point on the axis. And tan, remember, is our y coordinate over our x coordinate. So it's going to be a negative divided by a positive, which is a negative. So the only ratio which is positive in quadrant 4 will be the cosine. Which leads us to this next aspect of the unit circle, which says that cos is positive in quadrant 4. They're all positive in quadrant 1. Sine is positive in quadrant 2. And tan is positive in quadrant 3. And the easy way to remember that is CAST. Cast. Okay, so let's do a few examples of working out an angle using our unit circle. So let's find the sine of 120 degrees. Now we could use our calculator to do this. Sine 120 gives us root 3 over 2. Okay, but it's a very good idea to be able to use our unit circle because sometimes they in word form and the calculator won't give us that. The calculator will give us a decimal. So sometimes it's just good to be able to work out an angle using our unit circle. So let's draw a large enough unit circle just for this first example. Okay, so remember we always start on the positive x-axis and I want an angle of 120 degrees. Well, it's definitely not going to fit into the first quadrant because each quadrant only is a maximum of 90 degrees. So it's not going to fit into the first quadrant. So it'll stretch out into the second quadrant. So if we can imagine going all the way around 90, 100, 110, 120. So we're talking roughly, that doesn't add up, we're talking roughly this type of an angle here, 120 degrees. Now, 120 degrees is greater than 90. So I can't use our rules from our right angle triangle as in opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent. I can't use those because I have an angle greater than 120 degrees. So what I do is I look at this thing called our reference angle. This angle down here must be 60 degrees because remember a straight line is 180. So that angle in red down there must be 60 degrees. So how about I use 60 degrees? Let's get the sine of 60 degrees instead, because doesn't it still bring us to the same point? We're just going the wrong way, but we'll talk about that in a second. 60 degrees is my reference angle. So let's get the sine of 60 degrees. Now we should know by now that the sine of 60 is root 3 over 2 because that's one of our special angles from before. So these are the angles you were asked to learn. Sine 60 is root 3 over 2. And also please remember that they might give this to you in radians, as in sine pi over 3. It's the same thing. 60 degrees, pi over 3, they are the same thing. It's root 3 over 2. I'm just going to get rid of that. We don't need that for now. Okay, so the sine of 60 is root 3 over 2. But what's to differentiate that from being 60 in this quadrant? How do we know that's not the angle we're talking about? Well, we have to include one more piece of information. The sine of 60 is indeed root 3 over 2, but remember, we're in quadrant number 2. And what did we say about sine in quadrant number 2? In quadrant number 2, sine is positive. So our answer is plus root 3 over 2. So that's how we find the sine of an angle greater than 90 degrees. Let's have a look at one that brings us into quadrant 3. Let's have a look at the sine, we'll do the cosine of 225 degrees. So again, for this example, I'm doing a large enough unit circle. Now 225 degrees, well that's going to stretch us out into quadrant number 3. Remember, we're starting at the positive x-axis here. And if I want to go 225 degrees, and the reason I'm going counterclockwise, remember, is because I'm getting the cosine of plus 225 degrees, and positive angles are counterclockwise, negative angles are clockwise. So I'm going 225 degrees around. I'm going to completely bypass the first quadrant. I'm going to completely bypass the second quadrant, and it'll actually bring me halfway into the third quadrant. 225 degrees is this angle. Now again, what would my reference angle be? And our angle is always measured off the x-axis. So let's find out what our reference angle would be. Well, this here is our angle measured off the x-axis. Remember, this part is 180. So to get to 225, this part here must be 45. So our reference angle is 45 degrees. So the cosine of 45, well, we know the cosine of 45. Again, it's one of our special angles, and it's 1 over root 2. But what's to stop that from being 45 degrees in quadrant 1? We have to mention that we're in quadrant 3 getting 45 degrees. So in quadrant 3, the only thing that's positive in quadrant 3 is tan. We're not getting tan, we're getting the cosine. So cosine must be negative in quadrant 3. So our answer for the cosine of 225 will be the same as the cosine of 45, but in quadrant 3, so it'll be negative 1 over root 2. And that's how we use the unit circle to help us to find the sine, the cosine, or the tan of angles greater than 90 degrees. So that finishes your basic revision of the unit circle, and in our next video I'll be doing examples, just like I'll be doing examples of the previous stuff and exam paper questions. I'm going to go to this, we have basically, if you look on the right hand side of the screen there, we have the angle is 0 degrees, the sine is 0, the cosine is 1, and the tangent is 1. I'm going to view the coordinates, and I'm going to view the triangle. So basically, look at this, moving it around. Let's go up here, off the positive x-axis, we have 90 degrees. You can see on the left hand side the sine of 90 is 1 and the cosine of 90 is 0. What is that point at the top of that screen there? The point up there is the point 0, 1. So remember, cos is the x value. The x coordinate up there at 90 degrees is 0, so the cos of 90 should be 0, which is what it says on the right. The sine of 90 is 1. So that is how we use the unit circle. Now let's just bring it back to 0. Let's turn off the triangle and let's get angles greater. Let's go to 270. So 270, the coordinates of 270 are 0 on the x minus 1 on the y. So that means the cos of 270 should be 0 and the sine of 270 should be minus 1, which it is. Now I know that says minus 0 there, but sure, minus 0 and 0 are the same thing, so So that's how we use the unit circle. I mean, if I want to go to 45 degrees, it says 0.707 there, but you know that to be 1 over root 2 for sine, 1 over root 2 for cosine, and you know that the tan of 45 is 1, and as it says there on the unit circle, the tan of 45 is 1. So the important thing is that we measure our angle off the positive x-axis. So that means we're split up into 4 different quadrants. Alright, so we have quadrant number 1, which I'm in at the minute. Now I move into quadrant number 2, quadrant number 3, and then quadrant number 4. And we always try to go off the positive x-axis, and generally in a counterclockwise motion. If we go clockwise, our angle could be thought of as 320 degrees, or I could think of it as minus 40 degrees. It's 320 because to get there I could have gone all the way around here 320 degrees. Sorry, there. Or I could have just taken a shortcut and gone this way 40 degrees. But because I'm going the wrong way, it's minus 40. So the sine of 320 should be the same as the sine of minus 40. So that's how we use our unit circle. We don't want to. Okay, now we're going to move on to the sine rule and the area of a triangle. I think at this point you'll have noticed that there is a relationship between the angles and the sides of a triangle. And what we're going to do is we're going to try and come up with an actual formula that links our angles to the sides of our triangle. And this is going to be known as the sine rule. Now, just for some basic notation, you should remember that when we're drawing a triangle, we generally we're going to use the letters A, B and C here. The letters aren't important. What is important is our notation. So for the angle, I might call this the angle B. This is going to be our angle A. And this is going to be our angle C. And notice I've used capital letters to denote the angles. If up here we have the angle B, well then that means this side down here is the side B, and I'm using a small lowercase b for that. Over here we have the angle C. That means this is the side C, and again it's a lowercase c. And lastly then we have the angle A and the side A, lowercase a. Also we could call this the vertex C, the vertex A and the vertex B, but I'm not going to use them for the moment. Okay, whoops. Okay, so this is important. Remember the sides are So the relationship between these is known as the sine rule, and this is what the sine rule says. Let me just paste in the sine rule. The sine rule says that side A divided by the sine of the angle A will give us the exact same answer as B divided by the sine of the angle B, or the exact same as C divided by the sine of the angle C. Or we could also say that the sine of the angle A divided by side A will be the same as the sine of the angle B divided by side B, and the sine of the angle C divided by side C. So this is the sine rule, and it has to be sine of the angle, which is why it's called the sine rule. So we can't be saying A over cos A or B over cos B. It has to be sine. So what we want to do now is we want to do the proof of this, because you are required to know the proof. So to help us to do the proof, what we're going to do is we're going to draw another triangle. It's not a 90-degree triangle, it's not a right triangle. And on this triangle, what I'm going to do is I'm going to drop a line down perpendicularly to the side C through the angle C. And because that meets the angle C at a perpendicular, we know that these are now two right angled triangles. Now, because they're right angled triangles, I can use my basic sine, cos and tan rules to say that's, and actually, do you know, before I go any further, I'm going to call this h for the height of that line there. So the height of that line is h. Now, that means looking at the triangle only on the left. So if I just focus on this triangle for a moment, what I know is that sine of A is the opposite over the hypotenuse, h over b. Now I can isolate h and get that on its own by multiplying both sides by b. So I'd have b sine A is equal to h. And if I do the same thing for the triangle on the right, I can say that the sine B is equal to the opposite over the hypotenuse, which is h over A. Now again, I can isolate h on its own and I can multiply both sides by A, and I have A sine B is equal to h. So this is saying to me that h is A by the sine of B, but over here we're being told that h is B by the sine of A. They're the same h because they represent the same line in the triangle, so that means I can put these together and say that B sine A is the same as A sine B. And I now have an equation. B sine A is A sine B. And as with any equation, I can do whatever I like to both sides of the equation. And what I'm going to do is I'm going to divide both sides of this by sine A sine B. So if I divide the left by sine A sine B, I need to divide the right by sine A sine B. And before I go any further, I'll notice that the sine A and the sine A will cancel into each other once, and sine B will also divide into each other once. And what I'm left with is B over sine B is going to be the same as A over sine A. And I can do this again by drawing a different triangle and doing this with C and finding out what C is, but what else I'm going to end up with is that they're the same as C over sine C. And that is our sine rule. So it's very important for you to use the sine rule when you want to solve a triangle, when we need to know one side and the angle opposite. So that's what we need. We need to know one side at least and the angle opposite this side, as well as one other angle or side. So I'll say that one more time. To use the sine rule, we are going to need to know at least one side and the angle opposite this, as well as either another angle or side. So for example, let's have a look at this example. We have a triangle ABC where AB is 8. The angle BAC is 30 degrees, and the angle BCA is 40 degrees. So we should always try and draw a diagram because it's really helpful when you have a diagram to look at. So let's just do a sketch of this triangle. I'm just going to do a rough sketch, okay? It doesn't have to be an artist's impression of it. It just has to be a sketch. I'm going to have the sides A, B and C. So A, B and C. We know that the length of A to B, and that's the vertex A to B. So we have the triangle ABC. It goes A, B, C. So what I'll do, just to not confuse you, the length from A to B is A. The angle that goes from B through A to C, so from B through A to C, that's this angle here. That should say 30 degrees, sorry, is 30 degrees. And the angle that goes from B through C to A is 40 degrees. So there's our triangle. And we're going to use the sine rule to find BC. So we want the length of the line that goes from B to C. So I'm just going to call that X. Okay? So I'm going to use the sine rule. And remember, the sine rule says to me that one side divided by the sine of its angle is equal to another side divided by the sine of its angle. Or the sine of the angle divided by the side is the same as the sine of the other angle divided by its side. So we could use either or here, but we're going to use the one that makes it easier for us. Because the unknown I have is a side, I don't want the side to be the denominator in a fraction, because that makes it a tiny bit more awkward to solve. I'd like this side to be the numerator in the fraction, so I'm going to use the formulas on the left. So what I know is 8 over the sine of its angle, and remember his angle is 40. So 8 over sine 40 will be the same as x over sine 30. So to isolate x and to get x on its own, I'm going to multiply both sides by the sine of 30, and I'm going to have a sine 30 over sine 40 is equal to x. Okay, so x is equal to 8 sine 30 over sine 40. And if we just do that out in our calculator, and make sure your calculator is in degrees for this because our angles are in degrees, we're going to have x is equal to 6.22 centimeters. So in other words, BC is 6.22 centimeters. Okay, so that's using the sine rule when we want to find the length of one of the sides of a triangle. You might be saying, sure, I could just use Pythagoras' theorem, but remember this is not a right-angled triangle, so I can't use Pythagoras' theorem to help me find what the length of x. So that's why the sine rule is so useful to us. Another thing we can use is we can find the area of a triangle. So in your study of geometry from junior cert, you will have said that the area of a triangle is half the base by the perpendicular height. So if we apply that to what we know now, this is vertex A, B, C, which means this is the angle B. So again, let me drop down a perpendicular, call a H for the height of that line. Well, what I know is this side here is B and this side down here is A. So that means the area of the triangle would be half A by H, just half the base by the height. But we can see from this triangle, remember this is the side C, sine B is the opposite over the hypotenuse, H over C. So that means H is equal to C by the sine of B, multiplying both sides by C. So what I can do is, I can say it's half, instead of A by H, I can now say it's A by C sine B. So basically the area of a triangle, if I want to use trigonometry to find the area of a triangle, it's half two sides by the sine of the angle between them. So multiply our two sides together, multiplied by the sine of the angle between them, and half it, and that's how we can use trigonometry to find the area of a triangle. So you might see this written as a half AB sine C, a half AC sine B, or a half BC sine A. I think in the tables the one that they write is a half AB sine C, and that's what you'll have in exams with you. So that's your formula for finding the area of a triangle. So that's what we wanted to cover in this video. Basically, let me just do a quick example of doing that there. I'll draw out a triangle. 6 centimeters, 7 centimeters. And here's our angle A. We know that the area of this triangle is actually 12 centimeters squared. And we're asked to find the angle A correct to the nearest degree. So we know that the area is a half. Remember the product of the two sides, 6 by 7, by the sine of the angle between them. So a half 6 by 7 by sine A. That will give us the area of the triangle. But we actually know the area of the triangle already. So 12 is equal to half 6 by 7 by sine A. Doubling both sides to get rid of that half, I have 24 is equal to 6 by 7 by the sine of A. And it's just a case of rearranging here. I mean, you can rearrange this, dividing both sides by 6 by 7, etc., get A on its own. So basically A is going to be the inverse sine of 0.5714, which is what I'll get when I do 24 divided by 6 divided by 7. Okay, so it's 24 divided by 42, which gives us 0.714. And our inverse sine, so sine A is 0.5714. Maybe I'll just actually explain that. Sine A is 0.5714, and I got that from saying sine A is 24 divided by 42. The 42 came from 6 by 7. So sine A is 0.5714. I don't want to know what the sine of A is, I want to know what A itself is. So I need to get the inverse sine. And the inverse sine on our calculator, where our calculator in degrees turns out to be 34.8 degrees, but I was asked to give this correct to the nearest degree, so our answer is going to be 35 degrees. So that's how we can use the area of a triangle formula for finding the angle in a triangle, or for finding the area of a triangle when we know the angles on the sides. So after this we'll move on to the cosine rule. Okay, now we're going to have a look at the cosine rule. You've already learned the sine rule, but what we're going to do now is we're going to use the cosine rule. And the cosine rule is generally used to find the third side of a triangle when the other two sides and the included angle are given, or to solve a triangle when the lengths of the three sides are given. So we might want, once again, to find the third side of a triangle if we know two sides and an included angle. So what we'll use is known as the cosine rule. And the cosine rule states that a squared, and remember that's a lowercase a, so it represents the side of a triangle. So a squared is equal to b squared plus c squared minus 2bc, and so far all of these are lowercase letters, so they all represent sides of a triangle, minus 2bc cos a. And the important thing is that this angle and this side are opposite each other. So the cosine rule could also be written as b squared is equal to c squared plus a squared minus 2ca cos b. Again, they are opposite each other. And I'm sure you can guess the third one. It's going to be c squared is equal to a squared plus b squared minus 2ab cos c. And again, we have an angle at the end and a side at the start, which are the same letter. They're the angle and the side opposite each other. So that's important. So this is the cosine rule. And just like in the sine rule, you are required to know a proof. So what we're going to do now is we're going to have a look at a proof for this cosine rule. So once again, we're going to draw a triangle. And we're going to label some vertices and some sides. So this can be the vertex C, B, and A, which means this is the angle A, which means this is the side A, which means this is the side B, and down here we have the side C. And just like in our sine rule, we're going to drop down a line from C, perpendicular, creating two right angle triangles. Now, but the only difference is, I'm just going to get rid of this side C for a second. I'm going to give this a point. I'm going to call this the point D, okay? Just so I can talk about it as we go through it. So the only thing I'm going to do, I'm going to say, let CD be called H, just like we did in the sine rule. CD is called H, and let's call the length of the line AD, let's call that X. So from A to D is X. Now remember, the whole length of the bottom was C. So if that small part on the left is X, well then this part on the right must be C minus X. Okay, so we have everything we need now on the triangle. We have our triangle ABC. We have this new point D. And the bottom has become a length X and C minus X, because together they need to make C. Okay, let's use Pythagoras' theorem now on our two separate triangles. So I'm just going to highlight these two triangles just so we can talk about them differently. We're going to have our yellow triangle on the left, and we'll go with a green triangle on the right. So now, actually, just before I go any further with this proof, I'm just going to mention one thing over here on the right hand side. We're doing the cosine rule, and we've only one angle mentioned in the triangle, so I'm actually just going to get the cos of that angle just because we'll need it later on. The cos of A is the adjacent, which is X, over the hypotenuse, which is B. So cos X is equal to, cos A is equal to X over B. That means X is equal to B cos A. And I'm just filling that in now because we will need that later at some stage there. So X is equal to B cos A. Okay, let's use Pythagoras' theorem on the yellow triangle on the left. So what we know is X squared plus H squared will be equal to B squared, because that is Pythagoras' theorem. That's what Pythagoras' theorem says, that the length of the two smaller sides squared, the sum of the two smaller sides squared, is equal to the hypotenuse squared. Now notice that both triangles have a common side of H, so I'd like to isolate the H squared part, and we're going to have H squared is equal to B squared minus X squared. So we have H squared is equal to B squared minus X squared. Okay, looking at the triangle on the right, we have the two smaller sides squared, so we have a H squared plus a c minus x in a bracket, all squared, is equal to a squared. So once again, let's isolate the h squared. H squared is equal to a squared minus, and then in a bracket, c minus x squared. So h squared is equal to a squared minus c minus x squared. So remember, on the left we're saying h squared is one thing, on the right we're saying h squared is another thing, but they represent the same h because it's the side of a triangle. So that means these two sides are equal and we can equate them. B squared minus x squared is equal to a squared minus c minus x squared. So all that's really left for us to do is to multiply out the bracket on the right and see what we can tidy up. So let's do that. And remember, I'm going to ignore the minus for a minute. I'm going to do this all in its own separate bracket. It's going to be a c minus x by c minus x, which leaves us a squared minus, now inside the bracket, c by c is c squared, c by minus x is minus cx, minus x by c is minus cx, and minus x by minus x is plus x squared. So on the right we're left with a squared minus c squared minus 2cx plus x squared. And when I factor in that minus on the outside, we're going to have a squared minus c squared plus 2cx minus x squared. And now let's rewrite in the left hand side, b squared minus x squared. So this is where we're at now. It doesn't quite look like the cosine rule yet, but we've a bit more to do here. Okay, so looking at the cosine rule, the top one, it says a squared equals. So let's try and get it to look like that. I have an a squared here, so let's get rid of everything else that's with it. Let's add all of the things on the right to the left hand side. So we've b squared minus x squared already on the left. I'm going to add a c squared. I'm going to subtract a 2cx, and I'm going to add an x squared. So we're left with, larger writing, a squared is equal to b squared. We have a minus x squared, now plus x squared is gone. So a squared is equal to b squared plus c squared minus 2cx. And that's where we're at so far. It's starting to look a bit like the cosine rule. If you look, we've a squared equals b squared plus c squared minus 2bc cos a. And we have a squared equals b squared plus c squared minus 2cx. So it looks like it, but you might be wondering where to go from now. Well, remember earlier on, we mentioned that we were going to need this piece of information. X is actually equal to b cos a. So if I replace my x below with b cos a, what I have is a squared equals b squared plus c squared minus 2c b cos a instead of x. And just tidying that up just gives me a squared equals b squared plus c squared minus 2bc cos a. And that is the cosine rule. And the exact same can be true for b squared equals and c squared equals. So there are three cosine rules. A squared equals b squared plus c squared minus 2bc cos a. B squared equals c squared plus a squared minus 2ca cos b. Or c squared equals a squared plus b squared minus 2ab cos c. So that finishes the cosine rule for us. We'll do an example just to make sure you definitely understand it. So what I'm going to do is I'm just going to draw out a triangle here. So what we know is that this is an angle of 50 degrees. This side has a length of 10. This side has a length of 8. This is the vertex A, C, B. and we're looking for the length of the side CB, or the side A here that we have labelled with lowercase a. So basically I'm looking for the side A, so I want A equals. So which formula do you think I'm going to be using? Which variation of the cosine rule? It's going to be the a squared equals b squared one. So just so I'm not changing it when I go down, I'm just going to copy that and paste it. So this is the one we want. A squared is equal to the other two sides squared. So that's going to be my 10 squared and my 8 squared, minus 2 by b by c, minus 2 by 10 by a, by the cosine of the angle A. Now remember, if this is the side A, this is the angle A. They have to be opposite each other. So cosine 50. So A squared is equal to 100 plus 64. 2 by 10 is 20. By 8 is 160. So minus 160 cos 50. And the only way you're going to go wrong here is if you make a mistake with your algebra. Okay, so be very careful with it. A squared is equal to 164 minus 160. And if you do cos 50 degrees, make sure your calculator is in degrees. If you do cos 50 degrees in your calculator, you're going to get 0.6428. So working this out, we have a squared is equal to 61.15. That means a is equal to the square root of that, which gives us 7.8, correct to one decimal place. So we now know the length of the side A. And looking at it, 7.8 does make sense, considering one side is 10 and the other side is 8. An answer of 30 or 40 would have been unusual, so do always check, does your answer make sense? So that's us finished with the cosine rule.